In this video I'll be going over concavity and inflection points, and we'll begin with talking about concavity. So let's let f be a function that is differentiable over some interval I. If f prime is increasing, so if the derivative is increasing, we say that this is the function is concave up over that interval. If f prime is decreasing over the interval, we say that the function f is concave down over the interval. I accidentally typed a second concave there. All right, and then let's look at a graph that illustrates this idea. Actually, it's a series of graphs. So here, in the first one in the top left, we have a function, and what we can see is we have some tangent lines getting drawn along this function. So we see that everywhere between a and b, the slope of that tangent line is going to be positive. So we say that the derivative is always increasing. Because this is increasing, this is going to be a situation where the function is concave up. Moving to the right, each tangent line is going to have a negative slope until point B, when it's going to level off. But everywhere the derivative is decreasing, so we say that this is concave down. And then we have similar ideas for these last two graphs. One way to think about concavity is, how I've heard it described, is whether the function will hold water. So imagine we're pouring water down onto this graph. Now, what's going to happen is, because this graph is concave up, the water is going to kind of settle in into the bottom of this curve. On the flip side, if we were to pour water onto a graph that is shaped like this, that's concave down, the water is just going to roll off over to the side. So it's not going to hold the water. So one way to think about concavity is, if the function holds water, we say it's concave up. If the function does not hold water, or in other words, the water would kind of roll off, we would say it's concave down. So we want to see how we can test for concavity, and what you notice here is we're looking at what's happening with the first derivative. So if the first derivative is increasing, or if the first derivative is decreasing. So what we need to do is we actually need to take the derivative of the first derivative, or we need to be looking at the second derivative to test for concavity. So to find out whether a function is concave up or concave down over an interval, we say, or we want to let f be a function that is twice differentiable. This just means we can take the derivative twice over an interval. If that second derivative is positive for every value in the interval, then we say that this is concave up. If the second derivative is negative, we say that this is concave down. Okay, so we're going to do something quite similar to what we did to determine whether a function is increasing or decreasing over an interval when we were doing the first derivative test. So now we're going to take the second derivative of the function and test the intervals to see whether they give positive values or negative values for the function. And the last definition that we want to look at is something called an inflection point. So this is just saying when a function changes concavity from positive to negative, or negative to positive, that point, a, f of a, so I should kind of define everything here. So if f is continuous at some point a, and the concavity changes at that point, then the point a comma f of a is called an inflection point. So an inflection point is just the moment when the concavity changes from positive to negative or negative to positive. So looking at kind of a simple graph here, let's say my graph looks like this. So at this moment, somewhere around here, let's call that point A, the concavity changes from negative, so in this interval, the concavity is negative. Again, if we were to pour water down here, the water would just roll off. But then from A, let me make this a little more precise. But then from A and moving to the right, at this point, if we pour water, the graph will hold the water. So here we're going to say positive, so this would be concave up. And then similarly down. Okay, so kind of to summarize everything, if the second derivative, if the value of the function when we take the second derivative is positive, during that interval the function will be concave up. If the second derivative tells us that the values in the interval are negative, the function is going to be concave down. And wherever a function changes from concave down or from concave down to concave up, or vice versa, from concave up to concave down, we call that an inflection point. Okay, so let's look at one or two examples that can help illustrate this. So our first example says to find the intervals of concavity and the inflection points for the function f of x equals 5x to the fourth minus 20x cubed plus 10. So what we want to do is find the second derivative for this function. So to do that, we need to find the first derivative. So just using the power rule on the first two terms, we get 20x cubed minus 60x squared. And then let's find the second derivative as well. That's going to give us 60x squared minus 120x. All right, so what we want to do in order to find the concavity, we need to figure out when is the second derivative equal to 0. So we're going to set 60x squared minus 120x equal to 0, and then we're going to solve that equation. I factor out the 60x first. So we have two factors, set each factor equal to 0. I'm going to get x is equal to 0 and x is equal to, that's not correct, hang on, let me fix this. This will just be 2 here. Okay, so setting x minus 2 equal to 0, we get x is equal to 2. So we want to do a similar process to what we were doing with the first derivative. We're going to make a number line and plot these values on the number line. And these values could be where the function changes concavity. So we're just going to test values into the second derivative, into this right here. So how about if we test negative 1? Testing negative 1, I'm going to get positive 60 minus 120 times negative 1. That's also a positive number, so I get positive. So that tells us this is concave up in this interval. And then let's test, how about positive 1? I'm going to get 60 minus 120, so that's going to be a negative value. So that means this is concave down. And then I'll pick a positive number. How about, I'll just pick 10. When we pick 10, when we input 10 into the second derivative, I definitely get a positive value. So that tells us this is concave up in this interval. Okay, so because we're changing from concave up to concave down here, and then we change from concave down to concave up. So because there's a change at both of these points, that means that 0 and 2 give us inflection points. So what we're going to do is we're going to say, what's f of 0 in the original function? That's going to give us 10. So for our inflection point, the first one we have is 0, 10. And then I'm going to input 2 into the function. Inputting 2 into the function, well, I can't do that in my head. So 2 to the fourth is 16. 16 times 5 is 80. Minus 2 to the third is 8 times 20 is negative 160. Plus 10. I think that gives us negative 70. Okay, so the second inflection point is going to be 2 comma negative 70. So looking back at the question, find the intervals of concavity and the inflection point. So we have the inflection points. Those are here. And then for the intervals of concavity, we'll just write those in interval notation. So concave up, we're going to say it's going to be from negative infinity up until 0, and then union to infinity, and then concave down is that middle interval, 0 to 2. So here's the graph of our function, and I've labeled the 2 inflection points. We have one here and one here. So we can see that from the left of this point, the function is concave up. Again, if we were to pour water in here, it would hold the water, and then from 0 to 2, the water is going to fall off. But then from 2 all the way over, this is now concave up again. So hopefully this is making it more clear, connecting to what we just did in that last example. All right, let's do the same thing for this function. So find where the function is concave up and concave down, and then any inflection points. So again, let's find the first derivative. So we're going to have 4 times 1/12, which is 4/12, which is 1/3, x to the third, minus, again using the power rule, 3 times 1/3 is 1, so that's just x squared, plus 2 times 1/2 is just 1, so plus x, and then the derivative of a constant is 0. So there's the first derivative, and then the second derivative we'll end up with 3 times 1/3 is 1, so x squared minus 2x plus 1. So there's the second derivative. And again, if we want to find where this is concave up or concave down, we set that second derivative equal to 0 and solve the equation. And this factors to x minus 1, x minus 1. So the only point that we need to concern ourselves with here is 1. So looking to see what we have in each of these intervals. So we want to test values into the second derivative to see whether the intervals give positive or negative values. So to the left of 1, we can substitute, 0 makes the most sense. When we input 0 into the function, we're left with 1, which is positive. So that means here we're concave up. Now I'll input, some value to the to the right of 1. If I input 10, I get 100 minus 20 plus 1, that's a positive number. And again, this is concave up. So because there's no change in concavity here, that means that 1 is not an inflection point. So therefore, 1 is not an inflection point. Remember, a value is only an inflection point when it changes concavity at that point. So because we're concave up to the left and to the right of 1, not an inflection point. So there's no inflection point, and then we also want to find the intervals for concavity. Well, this is going to be concave up everywhere. So we're just going to say negative infinity to positive infinity. And this is confirmed by our graph. So let's take a look at that. But before we look at the graph, just consider this second derivative. that second derivative is getting squared. It's a polynomial getting squared. So if we were to graph that second derivative, that's just going to be a parabola. And any parabola with a positive leading coefficient is going to be a parabola opening upward. And look, that kind of confirms what's happening with the concavity. It's concave up everywhere. And again, because it's concave up everywhere, the concavity never changes. There's no inflection point. So let's look at the graph of the original function. So this is what our original function would look like, which was f of x equals 1 over 12 x to the fourth minus 1/3 x cubed plus 1/2 x squared plus 5. So this is just kind of looks like a parabola that flattens out a little bit down at the bottom, but still always concave up no matter where we're looking. The last thing to go over in this video is the second derivative test. And the second derivative test kind of gives us similar things with the first derivative test. If you remember, the first derivative test is we can use to figure out the local extrema for a function, and we can do that also with the second derivative. So suppose we have a first derivative that's equal to 0, and that the second derivative is continuous over the interval that contains that value c, which, remember, c here, because the first derivative is equal to 0, c would be the critical point. So if f double prime of c, or the second derivative of c, is greater than 0, then we have a local min. If f double prime is less than 0, we have a local max. And then if the second derivative equals 0, then the test is inconclusive. So again, this can give us similar information as the first derivative test. The reason that we might want to use the second derivative test is if we have a function that might have a lot of fractions when we take the first derivative, but if we take the second derivative, the derivative becomes much more simple. It becomes a simplified version and is easier to work with. That might be an instance when we want to use the second derivative test. So let's do a quick example to illustrate how this works. Alright, so let's let f of x equal 2x cubed plus 3x squared minus 12x minus 3. Let's use the second derivative test to find any local extrema for the function. So we need to find the first derivative and then the second derivative. First derivative, just using the power rule, we're going to have 6x squared plus 6x minus 12. Second derivative, we're going to get 12x plus 6. And then what the second derivative test is telling us is, well, if we want to look at the critical points, which are when the first derivative is equal to 0. And if you watched the previous video when we talked about the first derivative test, then we already did this problem. So if I factor out a 6, I get x squared plus x minus 2 is equal to 0. This factors to x plus 2, x minus 1. So the critical points are going to be x is equal to negative 2 and positive 1. So what the second derivative test is telling us is if we have these critical points, then when we input those critical points into the second derivative, that'll tell us some information. So f double prime of our first critical point, when I input negative 2, I get 12 times negative 2 plus 6. That's going to be equal to negative 18, which is less than 0. So what that tells us is because f double prime at negative 2 is less than 0, we have a local max at c. So what that means is local max at x is equal to negative 2. And then similarly, f double prime at 1. When we substitute 1 into the second derivative, we get 12 times 1 plus 6 is equal to 18, which is greater than 0. Now we're in the first instance up here. Let f double prime of c be greater than 0, which it is. Then we have a local min at x is equal to 1. And again, this function that we were working with was the same function that we had in the previous video, and we actually found the exact same conclusion, or we came to the same conclusion down here. So this is just a different way for us to find local mins and local maxes.